Are you starting to feel like a data analyst? We should be, right? Once we crunch some numbers. So have your calculators ready. We continue here with our example with our, I think we finished the health online example with the proportions, right? We calculated p hat 1, which is the proportion of population 1, and we calculated p hat 2. And I believe we continued and we finished this one by getting a confidence interval here, where they were both the lower and upper bounds in the box are both negative. So that automatically says we have a statistical difference. What does that truly mean? It means it's a meaningful difference. It means, right, it's not just random, it's meaningful. Right. And so in the context of the question, so, well, what was the question about? The question wants to know if there's a difference between the proportions of male and female internet users who use the internet to obtain health information. So are they constant? No, we conclude and go, no, there is a meaningful right? It's statistical difference to get into the decision making. So we are right here talking about how we would do this for a hypothesis test. For the hypothesis test, the denominator changes. So our standard error is different for the proportions than the confidence interval. It's when we aggregate these totals by the grand totals. We aggregate it, and it's, whoops, the reason we do that is because it's, the theory makes us do that because it says that the quantity in the denominator is normally distributed, right? So the difference is normally distributed with a mean of p1 hat subtract p2 hat and a standard deviation of the denominator. We call it the standard error, SE, standard error. Right. So we had these quantities, I believe we left off here. We're right where we left off. And please verify these. We had 0.1661 for P1 hat, 0.2193 for P hat 2. We calculated the standard error as being 0.01853. Yes, you can find it here. Yep. Okay, so we can carry on. We have our null. We need to state our null and alternative hypothesis, which is just going to be, the notation is H naught. H naught means initial, so it's our initial claim. The null hypothesis is our claim that we believe we want to test, and we want to test that the difference is equal to 0 versus, which is the same as, this is also, you can also write it as this, equals, versus HA, which is going to be the difference, is going to be, we want to do less than, which is, it's always a contradiction, right? It's always a contradiction. The two, they have to contradict one another. You may see it in the textbook where if this is equal, then this may be the same as greater than or equal. Just, it has to be the opposite. I always run them as being equal, but you may see it in the text where it will be completely opposite. It's greater than or equal versus less than. And that's the alternative. We then get our test statistic. That's our next step. And that's going to be a Z. All proportions are related to Z. All proportions are always, there's never a T. Don't try to mix the two. It's always with a Z. They're always normally distributed. And this is going to be the formula. Again, knowing which formula to write down. That right there should be worth 90% of the grade. knowing that's the formula for the test statistic. And so when you're writing these things out in the lab, make sure you state the formula like that in notation and then plug in your values, because this is so important right here. And then the conclusion. So always be focused on the method and the conclusion. And then the numbers are just all in between. It's funny because we go through, we go through elementary school and we go through high school even, calculating numbers and want to get the focus is getting the right number and getting that number, but it's actually, you want to shift them in thinking of more method. The method is more important. And of course the numbers are too, but you have to have that method first. You have to have the right method. And it's going to be 0.01853. And you can verify this. Please use your calculators to verify. Does anybody have a number? Test statistic. You have your calculators. You want to avoid the passive learning where you're just sitting back and reading. You want to actually, we learn this so well by doing. Yeah. Negative 2.7. Perfect. Yes, I get that too. Negative 2.87, and the third decimal was 1. Yes. Yeah, so we'll always try to carry at least to 3 decimal places for your intermediate steps and final steps. Always try to carry as many. You want to be that computer. So we could do the p-value this way, which is the p-value where we go is less than negative 2.871. We all know how to do this. You just look that up on the table. And we just go to the table, the standard normal table that everyone knows so well. Should hopefully you recognize it. So negative 2.87, so negative 2.8 right here, and then we go to the column 7. I'm going to ignore 1. It doesn't. The table doesn't go to 3 decimal places, but that's okay. This is a really good approximation. I get 0.0021. Everyone agree that's what the p-value would be? 0.0021. Is that considered a small p-value or a large p-value? Well, it's a probability, right? So in the world of hypothesis tests, is it strong evidence against the null or weak?
Strong.
It's strong, you bet. It's a very small number. And the smaller the p-value, the stronger the evidence against the null hypothesis. And what's the evidence? It's the test statistic, the negative that we just did. The evidence is the data that gave us that standardized score, negative 2.87. And it's a small p-value. Right away, we're going to reject the null hypothesis, right? Strong evidence against means reject. It was 0.0021. We could also do it the other way too, the critical value. The critical value with alpha equals 0.05 would be, you want to think of it, you would want the 95th percentile. This is the rejection region over here. That's the rejection region there. So the 95th percentile ends up being 1.645. You can look that up too. It's a reverse lookup. It's a reverse engineering lookup. You look reverse lookup. You could always do it this way. Remember our T table that we have. You can just simply go, well, here is 5% in the tail right here, right? That's 0.05. In the tail, if you go, instead of getting a degree of freedom, normal distribution has no degrees of freedom, but we do come down here to our infinity. And there it is there. You can grab it there, 1.645. It's just like a puzzle, okay? So that's our critical value. And we go, the critical value is 1.645. So in both cases, we have a small p-value, and the test statistic, you would take the absolute value. In this case, it's a one-sided test, so you would just take the absolute value, 2.871. You can see it's greater. In both cases, we reject. Whoops. Reject the null hypothesis, and we would conclude that there is a statistical difference. I'll stop and just take the square root, because remember, we just said that the variances and the standard deviations are related. So the textbook has a different method than this. Use this one. It works every time, and it's so much more straightforward. You have your F, your observed F value. You just literally take the largest of your two variances. So if population 1 variance is greater, then you put it in the numerator. If the population 1 is greater, you put it in the numerator, and then you put the smaller one of the two in the denominator. You have what is called the F ratio. We call it the observed F. This is the observed. Right? The F, just like what we just did, we had the observed Z value, and then we had the critical value. And when we have the critical value, anyone remember the difference? The critical value is the table value. That's from the table. So this is the observed value from the data. It's collected and calculated from the data. And the degrees of freedom, this F distribution has not 1 degree of freedom, it has 2 degrees of freedom for its function. And so what it is, the F is related, well, you've seen how the T is related to the Z normal distribution. F is related to the T distribution. Basically, if you have a T distribution and you square it, you have F distribution. And so when you have it, it looks like this. I teach data viz, so it's always nice to have a picture to see what it visually looks like. When you square the T distribution that was centered at 0, it had negative values and positive. If you square all those values, you're going to have all positive values. So your F value will always be positive. And what you do at this point is you have 2 degrees of freedom. You can look at the differences here when they're both equal to 1, right? So it's going to be n-1 from population 1 and n-2 from population 2. And you can see how as the degrees of freedom changes, you can see the curves. We have more area under the curve, where the curve would flatten the curve, and it becomes more flat. You can see with the blue, it's really becoming more flat. So as the degrees of freedom increase, there's all these different families of F distributions. Okay. And so what we do is we have the F table, and there are different F tables, but the one we're going to use the most is the alpha of 0.05. That's our significance level. And so what you do is you go, well, the numerator, the degrees of freedom from the population in the numerator is going to be right here. I'm going to blow this up so we can really see it. We use right here. And for the denominator, that's den, we use the column. So if df1 equals, let's say 2, this is an example, and df2 from the population is 4, then the F will equal, the critical value F will equal, so that would be 2 and 4 would be right here, 6.94. So you go to 2, that's the numerator, and then you go to the denominator. So whatever value you put in the numerator, you take its corresponding size and subtract 1, and then you do the same thing for the denominator. Very, very fits perfect. And then you just compare it. There's no p-values. Don't worry about p-values. Just compare it with the table. You can do the p-value like you would normally do with a t, but we're just going to grab the critical value and just compare the two. And we have a decision rule where if the observed value is greater than the critical value, what do? We reject the null hypothesis. Okay, so let's try a test. Very simple. These tests, the F test is very, very straightforward. We just go, okay, we're going to compare that they're equal. This is versus that the population 1 variance is greater than the second. And so this method, the formula here, when you use this formula, it works for any test. So which one is the largest? So this is going to be the observed S. So this is the observed value is going to be equal to which number should I put in the numerator? We have 2 standard deviations. Which value would I put in the numerator?
Yeah, 4.68.
4.68. And it says the larger. That's consistent with our method. So it's going to be S2 is going to go here because it's larger. 4.68, and we'll square it. And we'll put in the denominator the other one, 7/8. Good. Excellent. So long, remember, keep your data analyst skills focused on which formula, which method. The numbers are okay. You want to be careful, but think that that's the most important step is knowing this method, getting that set up. We then get our F, a value. Does anybody have a value for this? We want an F. This is the test statistic. It's the observed F. Yes. 2.8. 2.83. Anybody else? Which is 4. So let's find that. We'll find that critical value. That's why I denote it with a star. The critical value always has the star. Is this correct? No, it's wrong, right? I see some faces going, I can always tell. The whole room changes. It's good, but you're my monitors. Class monitors to keeping this straight. So this should be 5 minus 1. Good. This is good that you're seeing there. Let's make sure we have our method because it's all in the method, right? 4 goes with population 2, so it's the numerator. It was corresponding to 4.68. And it's population 1. This is why I'm getting myself mixed up, right? Because this should be 1 and 2, right? Yes. So let's get the critical value, F star. When you think about F's, any star, like T star, Z star, F star, always think of the table value. So we're going to get that F on 4 and 18 in that order. So 4 is the numerator, 18 is the denominator, and we just go and get that. So look at 4 right here, and 18 is the denominator. I believe it's that. Does that look okay? You guys can see it better than me probably. 2.93. 4 is the numerator, 18. And it fits. We will go 2.93. Okay. Close. Right? So sits F is not greater than F star, right? It's not. What's our conclusion? Remember, the method is really important and the conclusion. What do we conclude? Is there a difference between the two variances? No. No statistical difference.